So let me begin by saying I don't really do climate change adaptation research, but I have a strong interest in it. I was a little surprised to see myself on the speaker list, but I'm happy to come here and share with you what I know, but actually more importantly, learn from the rest of you as well. Okay, so I followed your six slide template very closely. So beginning with research questions, questions that motivate my own research include what processes are driving changes in the global snow and ice coverage, and in addition to the rather obvious effect of global warming, we have perhaps less obvious effects associated with changes in precipitation, changes in global dynamics and circulation patterns, and also changes that might affect the reflective properties of snow and ice, such as the deposition of light-absorbing impurities to snow, and also changes in the metamorphic state of the snow. So some related climate change adaptation questions that I am interested in, I don't really pursue, but I'm interested in, include how should communities that are reliant on glacial melt adapt to the disappearance of glaciers? And a related question would be how should communities adapt that rely on snow melt runoff and storage in aquifers, such as California, adapt to changing snow conditions? A first world problem or question that interests me is how will the ski industry adapt to changing snow conditions, relevant to a small subset of the global population. Another research question that my research focuses on is what are the radiative and the climate forcings of short-lived pollutants, especially in the Arctic. So I have a research focus on Arctic climate. And by short-lived pollutants, we're talking about aerosols, aerosol precursors, ozone precursors, and even methane. And a related climate change adaptation question is how will particulate matter air quality, especially PM 2.5 levels, be affected by climate change? All right, methods. So methods that I employ in my research include the development of radiative transfer models, especially for snow and ice, and inclusion of these models into global climate models, such as the Community Earth System model, in particular, a model that I use quite a bit. I also employ remote sensing measurements, especially of the cryosphere, to look at global changes. And also a little bit of in situ measurements of the snow, especially the snow optical properties. Here you're looking at a snow, on the bottom right, at a micro CT scan of snow, illustrating the ornate features of some of the crystals from which we can derive properties such as the specific surface area of snow. Okay, so some examples of research. So whereas my research might focus on the radiative and the climate impacts of changing snow cover, here our research was featured in Nature Geoscience a few years ago. But some climate change adaptation questions related to my other point about freshwater resource availability from glacial melt runoff. You can see that this topic has been in the news considerably in recent months. Questions such as topics such as the impact of Andean glacier retreat, especially in Peru and Bolivia, affecting regional security, and then also a very strong focus recently on the Tibetan Plateau. Studies pointing out that glacier retreat in this area has been about 15% over the past 50 years. And snow and glacial melt from this region, also called the third pole or the global water tower, provide potable water for about 1 billion people. So changes in water resources in this area are very important. And then just today in the New York Times, there was a story that elaborated on these Tibetan Plateau studies, concluding that by the end of the century, between 1/3 and 2/3 of the glaciers in this region, the third pole, will be gone by the end of the century, depending on the climate change scenario that is assumed. And then on the topic of aerosol transport, just in terms of how changing climate might be affecting air quality, this is some work that a student of mine did, showing that emissions from East Asia will likely be transported more effectively into the Arctic region in the future with no change in emission, just purely a transport phenomenon associated with alterations to the polar dome, a meteorological phenomenon known as the polar dome, and the Arctic front, where we have large sea ice loss, and this reduction leading to kind of a bulge in this transport barrier that we currently have that will facilitate transport of pollution more readily into the Arctic in the future. And then we've also done things like look at the climate change, the Arctic climate change impacts of aerosols, including black carbon and organic carbon from different regions, shown in the bottom right, and from different sectors, including the domestic energy sector, energy industry and waste, transport, and other sectors. So we're able to partition, or we apply modeling techniques to partition the radiative and climate effects of these different emissions, short-lived pollutants. Okay, in terms of teaching, I teach courses, I teach entry-level courses on climate change, including our changing atmosphere, and then courses in my department, including climate physics and radiative transfer, using these textbooks. Finally, in terms of civic engagement, I'm not that active, something I'd like to become more active in. The most active, or the most substantial component of civic engagement would include my work through the Arctic Council. And within the Arctic Council, there are these different umbrella organizations, including AMAP, the Arctic Monitoring and Assessment Program. I'm co-chairing a group, an expert group that focuses on the impact of short-lived climate forcers on Arctic climate. We're in the process of producing a new report that will be published in 2021. I've done a College of Engineering video on how wildfires affect climate. So there's a connection with Paige's research that we might not have been aware of. And then occasional media coverage. So that's it. Thank you very much.